It's, I'm not sure why we're short so many people, but oh well. So today we're going to get some housekeeping issues. We're going to finish off object detection relatively quickly. We're going to then begin talking about sequence models. So this is solving problems for which we have either a sequence of input or a sequence of output rather than a kind of a one-shot input or one-shot output. And then recurrent neural networks are a way to handle sequence models. We're going to start getting into those. And we'll talking about those for the next probably couple weeks. Okay? So CNNs and RNNs are the two major types of neural networks that are used. CNNs for two-dimensional information and RNNs for sequential. Let's talk about the housekeeping though. Assignment 3 grading, I haven't graded it. I've printed it out. And by the way, it looks really nice. There's a conversion you can do from Jupyter Notebook to LaTeX. And so, well, to PDF via LaTeX. It hides that step. And so these are nice looking printouts, I got to tell you. So I am looking forward to grading those. I hope to have them by on Wednesday, but it might not be until next Monday. Assignment 4 is out. You should have all gotten a Classroom for GitHub invitation for that, as you have in the past. That is, you can work either individually or in pairs. I assume you'd prefer to have that option of individually as well as in pairs, because I can imagine sometimes it's difficult to find the time to work with someone. So there is that option. And in that, we're going to be implementing, so we're not using PyTorch, we're not using FastAI libraries. You will be using NumPy in order to implement non-max suppression, which we're going to be talking about today. So kind of the final step we need for object detection. Due to suggestion from a student and also from the evaluations, I decided that a project makes sense. Okay, and you say, wait, we had like a syllabus at the beginning of the semester, half a semester ago, and there was no mention of a project. Why do I have to do a project? Or is that fair? And you don't have to do the project. So you could just stick with the syllabus as it was. We have the assignments, we have the scribing, we have the midterm, we have the final. This is just an option. And so as far as grading is concerned, it would be it would replace, so the midterm is worth 40%, it would replace 25%. So not 10%, but would be worth more than the final. So basically, this would convert the final from 40% to the final equals 15%, and the project equals 25%. But wait, there's more. Just so it's a no-lose proposition, it's really the better of the final and the project is worth 25%. So in fact, we can say that's the new formula. And if you don't want to do the project, it's just like it was before. Okay? So the project, the idea really is to, let me bring it up here. To give you more experience in doing an end-to-end implementation of something, really, right? So where it's a little less guided, and you will learn a lot, because that's really how most of the learning happens, is because you will fail along the way. And that's my experience, is that most learning happens through a succession of failing. And my job is to provide you a somewhat controlled environment for that failing. So the idea is you will work on a project with up to 3 team members. It'll be from now to the end of the semester. You would have to decide on the project by, I believe I said Monday, November 5th. So yeah, I think that's Monday. So you'll need to come up with the teams and at least a rough idea of what you're going to do. And then we'll just meet weekly, or at least have status updates weekly so I can find out where you are. And then the end deliverable is a document of some sort, maybe a Jupyter Notebook, maybe a Jupyter Notebook converted to PDF, who knows, which describes what you've done, the entire code, so that it can completely be reproduced. Okay? And then I have a bunch of different project ideas I'm not going to go through those here. If you look through and you have any specific questions, let me know now, and then I'm happy to go through in more detail individually. Yeah.
So you mentioned at the end, like Kaggle competition. So we can basically pick any competition on Kaggle.
I chose these ones, but I'd be open.
So as long as we like run it by you first.
Yeah, so as long as run it by me first. Something like MNIST, which is digit recognition, is just too well worn, so I would not do that one. But yeah, it would be interesting, I think, to do a current competition because there'd be a bunch of other people who are doing it as well online, and you're in the running to get some money too. So I don't take any percentage of your Kaggle winnings. Other questions? And so this is just a sketch of the problem. If you come to me, I can give you more information, including references to papers and things like that. Okay. All right. Let's see. I have not updated the syllabus to show the mention of the project. The project is kind of an addendum to the syllabus, let's say. I don't know why that won't erase. All right. The last thing, how many of you aren't going home for Thanksgiving? A few of you? All right. Well, I just wanted to offer that I have Thanksgiving at my house, and I'd be happy to have any of you over for Thanksgiving. The only proviso is I live in Redlands, which is 40 miles east of here, and so that might require either a drive, if you have a car, or if you take the train, which runs on Thanksgiving, out to San Bernardino, I'd be happy to come pick you up. So if you're interested, let me know. But you should have some place to go, as opposed to sitting and eating in turkey in the cafeteria. Okay. I don't understand why this line is here, and now it's there. All right. Clearly, there's more to learn about this. All right, so object detection. We talked about matching to ground truth, right? The fact that we are going to take a cell that has a high overlap. So the boundary of the cell, look and compute what the overlap is with ground truth objects. And if you have a large overlap, then I'm going to say that the particular ground truth object is associated with the cell. And if you have no overlap, then this cell should have no prediction. Okay, it's just background. This computation is independent of the predictions. Right? We are not using y hat here. We're not using the predicted bounding boxes. We're using ground truth bounding boxes and comparing those to cells, or what we might also call anchor boxes, which are predefined. It's these dotted lines right here, and they never change. Okay? And then that will give us a way to compute the loss, because then we know what y hats, right, what bounding box to compare against, and also what probability of class and your softmax of what class to have. Does that make sense? Okay. So, and now the black is gone. That's very weird. So the matching does not limit only one anchor box to match to a particular ground truth object, right? More than one cell, like for instance, here, we might have now I'm taking some liberties here, right? Because these are tiny cells, and according to my rule we just had, we don't have a large overlap. But just bear with me for a moment. Let's say we change that constant to be very small or something. But the idea is we have a red cell, a blue cell, and a green cell, all of which are making predictions, and all of which the loss function was happy to say, yes, these match. Okay? So it is actually, the loss function is trying to optimize each of these bounding boxes to match the ground truth bounding box, which is not shown here. But what this means is so it's not a problem for training. It's a problem for prediction, right? Because what that means is you feed in an image and you say, give me out all of the objects and their bounding boxes. Well, you're going to get for this dog 3 of them, right? With also probably slightly different probabilities of whether it's an object or not, and slightly different probabilities of how much it thinks it's a dog or not. Does that make sense? So, non-max suppression is the algorithm that we use to deal with this. And what we provide here is a heuristic. And this is the heuristic that you are going to be implementing for assignment 4. I read a recent paper that was interesting where basically they created a neural net whose job was to do non-max suppression. Okay? And so you just ran that basically as the tail end of your object detection, which created multiple bounding boxes.
Like instead of this heuristic.
Instead of what?
This heuristic.
Instead of this heuristic, yeah, this is an so this is an alternative in a recent paper. The fact is, though, the heuristic works pretty well. So the idea is, first, let's just get rid of all of the boxes. Okay, so I'm going to distinguish here. Cell is the rectangular, same-sized object here, right? It's our predefined area that is it's a predefined area. And then the boxes are the predictions. So the first thing we're going to do is discard all the boxes in the cells where we're not very sure that it's an object there or not. Okay? So that gets rid of a whole bunch of them. Like it gets rid of, right, all of these and lots of others. And then we choose the highest probability of an object. Okay? So here we would do the blue one. And we mark that as a prediction. So here we go. That's a winner, right? And then we look for all overlapping boxes, where overlap means with a certain amount of overlap, that predict the same class. Because it is possible you have sort of 2 objects, one on another, and you really want to show both of them, even though they have a high overlap. So it's important that they predict the same class. So if they overlap with, let's say, 0.45, and this 0.45, right, and this 0.4 are, I don't know, I'm not sure I'd call them hyper, I guess they're not really hyper, they are parameters. We'll just say that, right, which you might tune. So here, we've marked the blue one as a prediction, and now we're going to go through and we find that it has a high Jacquard index or a high intersection over union. So we get rid of that one, and we do the same thing with the green one. And we're left with the blue one. Right? Questions on this? Right. Part of what you're doing, by the way, I mean, this is a 4-line algorithm, and so like, why am I doing this as an assignment? You're doing it in NumPy and trying to be fast. Okay? So you're trying to vectorize and not kind of have a while loop and 4 loops. You will have a outer loop, but you shouldn't need to have any inner loops necessarily. Yes, you shouldn't need to have any inner loops, any explicit inner loops. The rest will be just matrix operations that you can work with. So it will also increase your familiarity with NumPy. really don't understand this. There we go. And I assume that means I can't erase, no, because there's nothing there. So, anyway. So now what we need are different cells. Okay? We have a problem if we have a bunch of small cells. Give me a problem. Yeah, unless you have a small object, you won't have high enough overlap. So small cells won't match big objects. And big cells won't match small objects. So you need small cells and big cells and medium-sized cells. So we're going to create a big cell, like that's the entire size. And we're going to switch and now call these anchor boxes. That's normally what they're called. Okay? So there's one. For a lot of pictures, there is one big object in it, right? And so this would be a good anchor box to have. And then we just go through and make, let's say, 2 by 2. Right? And then, let's say, 4 by 4. And so on, until we get it small enough that we think we're covering all possible small objects that we're interested in. Yeah. Okay. But there's more, right? So already we are overlapping cells, right? In our previous example, when we looked, we didn't overlap cells. We tiled our information. But now we have overlap between large ones and small ones. Well, we can also go ahead and make cells with different aspect ratios. So let's look at the green cell in the top left. Right? That's the total cell. Let's also make ourselves sort of a landscape version of that cell and a portrait version of that cell. Why? Tall, skinny things like, give me an example of a tall, skinny thing. What? A giraffe, yes. Those are tall. People normally come in that orientation, right? Whereas dogs come in this orientation, traditionally. So, or cars, stuff like that. So they'll be better suited to actually overlap particular objects. And that way, if we had, let's see if I can draw this. So here is, you tell me what you think this is. Okay, good, it's a car. All we need is one person to agree that it's a car. And then, that's a person, okay? But they're right on top of each other, the person standing in front of the car. And by having multiple orientations of anchor boxes, we can have one anchor box that prefers this one, and one anchor box that basically has a high overlap with this one. All right, any questions? All right, that's non-max suppression. There we go. Just one little stray right over here. I've said this before. I've said it before today, but I'm going to still say it again. Anchor boxes are not in the network. They're not in your ground truth. They're only in your loss function, okay, as a way to do matching, yeah.
So then, say you're trying to use this like network for predicting like an image that you haven't labeled yet. How would you extract some truth from the like anchor box without doing this non-max suppression? And if you're doing the non-max suppression, how do you do that without the anchor boxes?
Without getting?
How do you do the non-max suppression that's required to like get out some answer from your network without concepts of the anchor boxes? Because isn't the non-max suppression?
Okay. So the non-max suppression does not require anchor boxes. The non-max suppression is working on predictions. Okay? It's working on predicted boxes. I said the architecture does not know about anchor boxes, and that is not 100% true. Right? So this is 99% true. So if we go through and make all of those anchor boxes of different sizes and different orientations, we might end up with 1,000 anchor boxes. What is our neural network's output?
Wasn't it the box with three things? Probability.
So we have probability. We have the class probabilities, so it's a bunch of those. And we have our bounding box, which is 4 as well. So we've got this. How many of these do we have? We have 1,000 of these. So the neural network knows about anchor boxes only in the sense that it knows how many things it's predicting. Okay? And then your loss function is forcing it to specialize particular anchor boxes to particular indices of outputs to particular areas. Questions? Okay. All right, sequence models. Sequence models, well, you either have a sequence of input or a sequence of output. I suppose if you wanted, you could think of an image as a sequence of pixels. Yeah, you could do that. But there's a little bit, right? We'd lose a lot of information if we just looked at it as pixel 1, pixel 2, pixel 3, pixel 4, kind of on and on. We would lose the spatial information that's present. But there are a lot of examples of problems that have a non-fixed input size or a non-fixed output size. An example, if you're dealing with text, let's say you're dealing with, because it's an example that'll come up later, IMDb reviews. Okay? Some of them are very short. This movie sucks, right? Some can be a lot longer. And one way you could do it is figure out the maximum you might ever want, and then go ahead and pad out anything else. But let's just look at some problems that are sequence models. So here's a many to one sequence model, an IMDb review, which let's say our problem is we're going to take this sequence of words. So we have word 1, word 2, word 3, all the way to here, you know, word 102. Through 134. And the question is it a positive or negative review? So is it a sequence of outputs? No, it's just sigmoid, presumably, right? But we definitely have a sequence of inputs. So we want to, that's a good example. Another example, one to many. I give you a picture, and I want to know a caption for it. Tell me what is going on in this picture. Okay? The man at bat readies to swing at the pitch while the umpire looks on. All right. Now we probably have a CNN, right, involved here too to deal with the image part of this. But we're going to also have to deal with the sequence part to get the output. Right? We don't know how long this is supposed to be, how many words the output is, right? A priori, we don't know. It's the network will figure out, and the ground truth will tell us kind of how long these things should be. Many to same. So, right, we did many to one, one to many. Many to same is many to many, but exactly the same number of inputs as outputs. So an example might be here. We put a sentence, the quick brown fox jumps over the lazy dog's back, and then we want to designate the part of speech for every one of the words. So we have a one-to-one correspondence between input and output, and we say it's an article, an adjective, a noun, a verb, and so on. It's not going to actually be outputting capital A-R-T-I-C-L-E, right? What would we be outputting here? At each output sequence. So let's call this y hat I'm going to use angle brackets 1. This is y hat, angle brackets 2. So what is the type that's coming out here, let's say, for a y hat?
Probably like a one-hot encoding, like classifying it as a speech.
That seems, so a one-hot encoding, so really a softmax over all the parts of speech, our limited number of parts of speech. Right? So we'd have, let's say, a softmax. So y hat at I equals softmax over all part of speech, all the parts of speech, right? The 10 or 15 or however many there are. There's certainly not that many. Yeah.
So you mean like over all parts of speech, are you saying the softmax over the number of articles that it can be?
I'm going to say what we have is, let's say we're going to say 0 is article, 1 is adjective, 2 is noun, 3 is verb, and then we're going to do a soft one-hot encoding, right? Our ground truth is going to be a one-hot encoding, where we say this is a noun, so it's 0, 0, 1, 0. Our prediction, right, so let's say our y might be 0, 0, 1, 0, our y hat, and let's say this is y of some k, might be 0.2, 0.1, 0.6, 0.1. Yep. While we're talking about it, what about the input? Give me something that might work, and let's not even, or that we're brainstorming now, right? I won't judge too harshly.
You can break up a sentence in terms of sequences of words in order to maintain the dependencies.
Well, okay, so sequences of words. What I had on the previous slide was, not this one here, looking at the idea of having word 1, word 2, word 3 as the inputs, right? And in fact, I said, so since I want the number of inputs to equal the number of outputs, I want each input to be a word. Okay? So we know that. We know that x of I is a word. The question is, how are we going to represent it? I can give you one. We'll use no, it's just too silly. Go ahead.
Do like a one-hot vector, and then which is like as long or has as many elements as one of the words that your dictionary has.
So this would be a big dictionary. Dictionary of how many words people normally use? What's an order of it? Is it 500? Is it 500,000? Yeah, somewhere. I would guess most people have a working vocabulary of 20,000 maybe, certainly under 100,000. So let's say we did 50K. Where would we come up with this dictionary? Say it again. We could use Oxford Dictionary. There's an easier way though. Go ahead.
If your data set was a bunch of common, uses of words, you could say that we're going to say this is all the
Yeah,
words.
that's pretty reasonable. So take your data set, take your corpus, and pick the 50,000 most common words. Or maybe pick all the words and throw away the ones that only occur, 3 times, assuming you have a large set. And so we'll just get a giant one-hot encoding for each word. Okay, so let's say we have, V is 5023 and Fox is 32. Then our input here would be, so X 4 would be 0, 0, 1, and this is at index 32, right? And that's how we do it. The fact is, when you have a one-hot encoding, and you know there's a one-hot encoding, you can do some tricks when you're doing matrix multiplication with your weights, right? So if you have a weight matrix times your x, and you know it's one-hot encoded, maybe you don't actually even store it as 0, 0, a bunch of ones. You just store it as 32. And then it says, just go ahead and take the 32nd row, right, of the weight matrix. Okay, many to many. So many to same is my terminology. I haven't seen anyone else use that. People just talk about many to many, and then they say, well, it's many to many where the size of x equals the size of y, right? Or many to many where they're different sizes. So we want to translate the quick round fox jumps over the lazy dogs back into Russian, Bistra korinich vaya lisa, and so on. And so here we've got different numbers of words. Right here we've got 4, 8, 10. And here we've got 3, 4, 5, 6, 7, 8, 9. 5, 6, 7, 8. So clearly different. Could be more, could be less. We've seen a lot of examples of text because text is naturally sequential and text is just RNNs are used a lot for text. But could be also used for audio. So you've got an audio sample. I'm providing this because why do we have 2 of these for audio sample? Why do audio samples normally come in pairs? Because you have 2 ears, right? So we have the left channel and the right channel, commonly. And so we want to generate the text, which is, by the way, there is no correspondence between this. This is just like a waveform I got on Google Images. Doesn't actually say this, but it could. And I chose a waveform that looked more like speech than like music, let's say. So that's many to many. We know what our output is, right? Our output is this text. What is our input? That is, what's an x? What's it equal?
Some small part.
Yeah, let's say there's x at I. Okay, so it'll be some sample. Maybe we'll do some pre-processing on this, right? We do 5 millisecond chunks or something, and we, there are a lot of different ways we could do it. We probably don't want to be feeding in every single, if it's 22 kilohertz, every single sample there that we want. But theoretically we could. Got to get my scrolling better. We could go the other way. So this is also many to many. Clearly our y's are much larger than our x's here. And we actually come out with, right, this is just text to speech. So we know about this from, give me some text to speech examples. What's that? Say again? Google pronunciation. Alexa, right? When it talks to you and says that the weather today is whatever. Coming back here a second. So I remember being in college and finding, I don't remember where because I didn't find it on the internet, but finding that Digital Equipment Corporation, which no longer exists anymore, had done some speech to text, so speech recognition. And there was a phone number you could actually call and try out the speech recognition. Get this, what it could do. It could do speaker independent recognition of the 10 digits. So you could say 953, and it would recognize that you said, actually, I don't even know if you could do them together. I think you had to say 9, and then it would recognize 9, and then 5, and then 5, and then 3, and then 3. All right? And at the time, that was pretty cool. All right. Oh, let me give you one more example. So this would be many to one. And this is what's called a language model. So in a language model, you provide some words like the, quick, brown, and you're trying to provide the probability of the next word. So you're basically looking, in this case, of the probability of y4 given y1, then y2, then y3. So this can be a complicated problem, right? There has to probably be, if you want to be really good at this, some real understanding of language, of the language here. Richie? Well, I mean, the way we're doing it is or we are going to be doing this is with a recurrent neural net, which is a time series, right? And I'm going to say models for image recognition, okay, like ResNet 34 for ImageNet, are very good for transfer learning in image domains, right? Language models are very good for transfer learning in language domains. So rather than starting with nothing and training a neural network from scratch, start with a recurrent neural network that addresses the language model, so that is a language model, and then modify that to do what you want it to do and continue training it, right? So in your modification, you'll probably have some new layers with some randomly initialized weights, go through, do some training, update those weights. Once that's done, maybe unfreeze the other layers to do some more training on stuff. But it's a very powerful technique and not very much used in the language realm. So worth knowing about. So language model be very handy. All right, so recurrent neural networks, what do we want? Well, we know we want variable length input or output. We'd also like to keep some state information. As we process, let's say, so the way we want to think about it is we're going to have a sequence. We're going to get given the first input, x angle bracket 1, and we're going to do some processing, and then we're going to go from this way, x1, and then we'll get given x2, and then we'll get given x3. And maybe when we get x1, we're going to output y1 immediately. We'll see that there are some options there. But that's a common kind of a recurrent neural network where we get an input and we produce an output. And then we go to the next time step, get an input, produce an output. The thing is, though, so if we have at step 1 an input coming in and we do an output here, right? This output is y hat 1. This is x1. And now, at time 2, we have x2, and we have output y hat 2. Are these independent? No. I mean, if we wanted them to be independent, it'd be really simple. Create one neural network which just has an input, some number of layers, and an output, and feed your input there. And then just go ahead and feed your next input in and get your output, get your next input in and get your output. What are we missing here? Context. We've forgotten everything. We're only, in fact, looking at the single word. There's no other state. So all we can do is look at the particular input we have and figure out what output we want. And we have no context, no state information. So we want state information. What we want is to actually have some state information that gets propagated along here to some new state information. And then that's going to get propagated, and so on. And that's the idea of a recurrent neural net. The state information in the memory is really saying sort of the same thing. Long-term dependencies is sort of the same thing as well, right? It's memory or it's state information. But we just have to keep in mind that sometimes we need information from fairly far in the past. Okay? I'll give you a language model example. Let's say, so we have something like, I was born in France. This is not autobiographical, I'm just making it up. I like to eat chocolate, even as a young boy. Maybe it's especially as a young boy. And then we have some other sets of words, and eventually, let's say, of course, I'm fluent in, what's the word? French, probably. How far back did we need to go? Back to where we said I was born in France, which could be an unknown amount of time here, right? We have a long article, like my long autobiography, and it ends with, right? The conclusion to the autobiography is, of course, I'm fluent in French. So much of the time, especially when you're doing language modeling, your state information that you need is relatively close. Other times, it can be very far away. And so we're going to have to come up with a way that we can easily deal with far away, with providing state information from far away, and yet still be able to train this sucker. Okay? Because theoretically, just this information here, the idea that we have some state, and we pass it on, and we pass it on, and we pass it on, there's a connection between the born in France and the speaking French through this state information here. We just need to make sure that that information can actually be maintained, and when we do backpropagation, that we can train it. Yeah, Drew?
Can you leverage something like a knowledge graph? Like build a knowledge graph out of sentences and start, chunking information, like the location, user?
Wouldn't it be better, rather than coming up with a knowledge graph, just to say, hey, neural network, if you think a knowledge graph would be a good thing, go ahead and make it. There are cases where you need a lot of knowledge. I just saw so Geoffrey Hinton is at University of Toronto, and he's a big deep learning guy, right? Like from way back when, like he's on the original paper that says backpropagation, right? Here's how to do backpropagation. Anyway, so he had an interesting sentence that's going to require like a knowledge graph for something deeper. So here's what it is. Something like this. I tried to put the lamp in the suitcase, but it was too big. Does that sentence make sense? And what's the it here? The lamp. But if I say it was too small, what's the it? The suitcase. So we have to have some knowledge there in order to do that, right? We have to know that you put small things in big things. So that's an how would you even test to see whether your language model knew which it was? Right? It can predict the it. Yeah? Have this be blank? The problem is our language model works whether it's big or small. So here's what we do. Translate this, right? Like we saw the English to Russian translation. The way you do translation is basically model this, right? So understand the structure of this, and then convert it to the other language is commonly how it's done. So if you convert to another language, the good thing is lamp and suitcase, by the way, I'm fluent in French, are different genders that we call it. Yeah, I can only remember the French word. So different genders. So it would look different in French as to whether we're referring to the suitcase or the lamp. Okay, so we could tell whether I understood that or not. So in order to correctly do language modeling, you might definitely need to have some deep understanding. Okay. All right, recurrent neural networks. Let's focus on the word recurrent. And let's go back to looking at, from discrete math, recurrence relations. Right? So recurrence relations are equations. They recursively define a sequence of values. Best known example that everyone uses is Fibonacci, exactly. So we say Fibonacci of t equals Fibonacci t minus 1 plus Fibonacci t minus 2. And we need something else, right? Whenever we have recursion, we always need base case. How many base cases do we need? 2, because we're looking back 2 in time. So we'll say f of 0 equals f of 1 equals 1. That's a recurrence relation. Let's come up with another recurrence relation. And you tell me what this actually is. So I'm going to say what might this represent? And actually, we'll just define k equals 0.04. P0 equals 1,000. Some population growth model. What if I say this, if I add that? Yeah, it's a money growth model, right? So this is basically how your money grows at 4% compounded periodically. Right? How long does it take to double? How many time periods? You were on a desert island. Give me a number, roughly. Why 18?
There's like a rule where you
I love it. Rule of 72, yes. This is actually something you should know. Okay? So the rule of 72 says take 72 and divide by your interest rate. And it's the number of periods, normally years, to double. Okay? It's like very useful so that you can come up with that number 18 as opposed to log 2 over log k plus 1 bit, which would work. So. All right, and let's just look at an example of the rule of 72. Just while we're here, we will come back to our recurrences in a moment. So Berkshire Hathaway stock. In 92, it was around $18,000 per share, which seemed like a lot. In 2018, it's about $300,000 per share. What is the growth rate per year of this, roughly? So 2018 minus 92 is how many years? 26? Actually, it was more like 93, let's say. So let's say 25 years. And how much bigger has it gotten, approximately? Approximately 16 times. How many doublings is 16? 4 doublings. Okay, so each doubling, let's say, took a same amount of time. So it's about how many years to double? Yeah, so approximately 6 years per doubling. So that tells us, if it takes 6 years to double, what interest rate? About 12%. So it's compounded about 12% for the last 25 years. Okay. And just as an aside, I was first heard about Berkshire Hathaway stock when it was at $5,000. Okay, and they talked about this meteoric, rise it had had since the late 60s when it was at $100 and it went up to 5,000. It's like, wow, that would have been a really cool stock to get into. But I knew $5,000, I guess I missed it. So. Okay. Okay, so we got a simple neural network. Here's what we're going to look at. We've got square, which is our input, triangle is our output, and circle is an activation. It's some internal layer. Right? And we have an operation on our arrows here. So we have an operation that does a matrix multiply followed by some G, right? Could be a sigmoid or a ReLU or some nonlinearity. And then our activation, and then we have some, again, operation with a matrix multiply with a weight matrix, and then some activation function. So a recurrent neural network, we're going to use the same type of legend here, basically, right? Squares, our input, triangles, our output, circles, our internal. And here's basically a recurrent neural network. So we're going to take x1 and do our standard matrix multiply and some particular activation function on that. And that's going to give us some state, which we're going to call H. H for if I said S, what would it be for? State. H is for hidden. Yeah, H is hidden. Okay? So time step 1, we're going to feed in this x1, do this calculation, and then do matrix multiply on that hidden state and an activation function and come up with this y hat 1. So this is just our normal neural net that we saw on the previous slide, on its side. But then what we're going to do is we're going to say, okay, this state information we're going to pass on to the next time step state information, going through a matrix multiply and an activation function. And also, and I'm not really showing it here, but we've got a tiny little so we've got a plus operation. Some sort of a combination operation we need to do to take our two inputs into here, right? Because we got two errors coming in. We've got our H coming in that gets weighted and then an activation function, and we've got now our x2 that comes in. And then we spit out a y2 in the same way. And we just keep going until we've processed all of our input. The problem with this explicit formulation is there's some bounded size we can have here, right? I mean, if we create, we have to know how many of these to create. We're going to see we can actually just use a for loop to go as long as we want. Just keep going while there's input. It's a possibility. There's a key thing to notice here, though, and that is the weights that we're going to use for our incoming x's are going to be the same at every time step. Is that reasonable? I mean, it's not clear why we want to treat the first word different from the fourth word, right? There might be some state that causes us to treat it differently, but just the fact that it's the beginning, we don't necessarily need that here, right? This state can somehow reflect the fact that it's the beginning. But we would just want to do the same thing to each of the inputs, and we want to do the same thing to each of the outputs. So from x to hidden, same weight matrix every time. From hidden to y, same matrix every time. And then from hidden to hidden, same matrix every time. Does that make sense? So what we're doing is we're basically taking right here, this is the same diagram. The only real difference is we have a matrix here that's the same as the matrix here. And we have a matrix here that's the same as this matrix here. And we have a matrix here that's the same as that matrix here. Okay? So we're just providing a mechanism for passing some state information from one time step to the next time step. And when we say time step, this isn't really time related, right? If we're talking audio, yes, it's probably time. But if we're talking text, it's not time, it's just order, order of the word. So it's a sequence. Often I'll use time for that horizontal axis, right, as a sequence. But in some cases, that's really just, that's not correct. All right, we can rewrite this. We can rewrite this by taking advantage of the similarities between here and here. Right? So we can say x1 feeds into h1, which goes to y hat 1. And then this goes to, and let's just draw a big box to represent this. And so we'll have, let's say, hi outputs y hat at I, and takes as input x I, and we need to somehow represent the fact that we are kind of doing this multiple times. So one way we could do that would be, let's say, have that we kind of repeat this. delayed by one time step. Right? So we can repeat this over and over again. So, and I guess we'll show this going up there. Okay. So this diagram is okay, but we still got some duplication, right? We've got this duplication. No, we're not gonna, I'm gonna change this slightly. So this arrow is going away, and this is what we're doing. We're actually going to have this arrow go up and over and down like that with a delay here. Okay, so this is delay. One time step. And so there's no strict limit here in terms of this diagram of how long this is, which makes sense. We can have very long text, we can have short text, we can have long audio, we can have short audio, and so on. Anything bother you about this? Is it as concise as it could be?
I don't know if this is an accurate volume, but it does disconcert me that it looks like you're adding H1 to every single time step.
Oh. It kind of looks that way, and I'm going to try to fix that in a diagram. Well, I have a way to fix it, so let's see. And that is, let's put x1 in the diagram too. Okay, because to my mind, the x1 and the xi's look pretty similar. So let's have h at I outputting to y hat at I, taking as input x I, and then this getting fed in to here with a delay. This is missing something, though. What's it missing? Yeah, it's missing a base case. Another way to think about it, what's our initial hidden state? So we need some initial h at 0 that we will feed in. And I know it looks like both of them are coming in, but we're going to just have to keep in mind this is our base case that's 0, and this is everything past 0. So, okay, we put an initial state, and guess what everyone uses? Zeros. Zeros plural? What is this? What is h of I? How are we representing that? It's a what? It's a vector. It's a bunch of numbers, right? So this is going to be, I'm not going to put an arrow in that because that would be confusing. And I'm sorry I erased that. Okay, so let's see. H, really h at I, is a vector with a bunch of values, right? It's basically like a bunch of neurons, right? It's just a bunch of values. How big should this be? So we need it large enough to maintain the needed state. Or another word for that is it's a hyperparameter that you'll tune, right? You'll figure out. Could be 100, 200. On that order, it's probably, you know, it's not a million. Yeah.
This is the output of the activation function.
Well, we have 3 different activation functions running here, right? There's an activation function from xi to h. There's an activation function that goes from h to y. And there's an activation function that goes from h at I to h at I plus 1. Okay? three weight matrices, 3 biases, 3 activation functions, potentially. Commonly, this is a ReLU. This one is commonly a sigmoid or a softmax. And this one that goes around out of here is, does anyone know? Normally back to old 10H. Okay? And we'll talk about a reason for that later.
It looks like in your formula they're using the same activation function for the combination of your recurrence and your so like your GH. You don't actually have a separate 10H value for you. Is GH in this example like we're going to do 10H or something else?
G of H is 10H.
Okay, so you don't apply a separate activation function at the inputs.
We have for the inputs a ReLU coming in here.
So like, if you look at the formula for RN on the slide, you have H and T GH times weights times H minus MS1 plus weights times X DH, and those are all added together linearly and then through a single application.
Oh, we are missing a ReLU here. You're right. We could have a ReLU here, but we don't need it. So, yeah, this is there. There are more than one way to look at that. We could certainly have a G of X here. It's not going to change too much, you know. So let's look at our formula, right? H of T is G of H, which I just told you is probably a 10H. We have a weight matrix, HH, so that's from H to H, of H of T minus 1. Plus, and this is just some combination we're doing here of the two inputs, plus our weight matrix HXXT, and let me just explain what seems like a funny wording for that. So when we have HX, so this X is close to this X, and this gives us roughly an H. So this is saying we're getting an H. Our output's an H and our input's an X. Okay? And then we've got our bias for the 8. Yeah. We should really throw in here. If we're going to throw in the G, we should throw in a B sub X here too. And then our Y output is GY times our weight matrix. Y is output, H is input, H of T plus BY. So what are we learning? We do our gradient descent. What's being learned here? Say again? 3 matrices and 3 biases. So what we're learning three matrices, 3 biases. One could have more layers in your hidden so that you could build up higher level features. So you'd actually have X coming in, and you'd have H, and you'd have K, let's call it. So if we have 2 of these, and then we could come out and around and back down like we did before. And so that's not really what I want to show. I'll show it unrolled. So we could have a set of one hidden layer here where we're passing state from that hidden layer across to the right through time. And then on top of that, another hidden layer that's passing information across to the right through time. So we could be keeping lower level features here, higher level features here. What's the sort of state information we might want to keep for, let's look at one of these problems before. Here, let's say we we see the quick brown fox. Okay? What might we remember to predict that the next word, say we don't even have this information here. So we have article, adjective, adjective, noun, and we get to jumps. But let's say actually, we're doing prediction now, okay? And we happen to get a word that wasn't in our dictionary. So we get a word like blurches, okay? Not in our dictionary. So that word itself, we're not going to be able to have somehow memorized what verbs look like. Why might we think it's a verb and not a preposition? No, not a preposition. Let's say a article. Because what? Well, we don't have a verb yet. We might have a verb later on. But how do we know that this is more likely to be a verb than an article? It follows a noun. So what state information we might want to keep from this state to this state? That we just saw a noun. Pardon me? Louder? Not in the output. We want to keep it in our H, right? So imagine if we were designing this by hand, we might say one of our 100 values in our hidden state is going to represent the kind of the last word we saw. We are not doing prediction for this problem, right? This problem, we're given our input, and we're trying to come up with what the type of speech is, what the part of speech. How do I know fox is a noun? It's in my dictionary, thank goodness. And I have this big language model, and it somehow knows that foxes and horses and other things, in fact, it knows it good enough to output that it's a noun. Okay? So it's going to know it somehow. Other information you might want to keep, you mentioned some state. Or whether there's a verb. Have we already seen a verb? Right? If we haven't yet seen a verb, then it's more likely stuff to come is a verb. That somewhere in there's going to be a verb. Okay? So there's a lot of state information that we might want to keep. Thank goodness we don't have to figure out what it is. Any questions? All right, I will be in my office all afternoon till 6 or something. So have a good afternoon. See you on Wednesday.